Before I talk about net change, I want to talk about net area. So far, we've been talking about only positive functions. So we said that if you have a function f of x, which is positive, meaning it's above the x-axis, within a certain interval from a to b, then this definite integral would be equal this area. The area above the x-axis, below the curve, between the two vertical lines, x equals a and x equals b. Okay. Now, what if f of x is sometimes negative, sometimes positive? What if f of x is a curve that goes above and below the x-axis? So something like this. Let's say it's something like this. So f of x is a function that within the range from x equals a to x equals b, within this range, sometimes it's above the x-axis, sometimes it's below the x-axis, then goes above, then goes below. So it's not always positive. So what would integral from a to b of f of x dx represent in this case? Then it would be something called the net area. That is, if this area here, if I call that A1, and this area here, if I call it A2, and this one, if I call it A3, and this one here, if I call that A4, then the definite integral from a to b of f of x dx would be, notice that a1, a2, a3, a4, all of them are positive numbers because these are areas. An area cannot be a negative number. So a1, a2, a3, a4, all of them are positive numbers. However, this integral, the definite integral, is not the sum of these areas. It's going to be the sum of the areas that are above the x-axis, that is a1 and a3, minus the sum of the areas that are below the x-axis, that is minus a1 plus a2. Or I can also say that it's a1 plus a3 minus a2 minus a4. So that's what I mean by net area. Net area. So it's not the area trapped between the curve and the x-axis. It is the net area. It's the sum of the areas above the x-axis minus sum of the areas below the x-axis. So do we understand the idea of net area? If x is positive, like in this case, the net area is area. But if x is sometimes negative, then the net area has a different meaning. Okay. Now, what is net change? So I'm going to begin with an example about population. Imagine you have a function pt, and this function gives you the population of a certain region during a certain time. That is, for example, let's say t equals 0 represents the year 1950, and then t equal 1 represents the year 1951, and t equals 2 represents the year 1952, and so on. So for example, t equals 50 would represent the year 2000. So if I plug in 0 in this function, that would be the population in the year 1950. If I plug in, for example, 10 into this function, that would be the population in the year 1960. So this gives you the total population. at any point at any year since 1950. Now, if you're looking for the net change within a certain period, so you want to know how the population changed, the net change from the year 1950 up to the year 2000. Then you're basically looking for the population in the year 2000 minus the population in the year 1950. That would be the net change, which could be positive, could be negative. If the population in 2000 is greater than the population in 1950, then this is going to be positive. Or I have to actually plug in 50 for 2000 and plug in 0 for 1950. So if the population in 2000 is greater than the population in 1950, you're going to get positive. Otherwise, you're going to get negative. Or imagine you want to know the net change in population within the range from 1960 to 1970. Yes, then you would have to figure out what the population was in 1970 minus what the population was in 1960, subtract from each other, and that would be the net change in population. Again, could be positive, could be negative, because it depends on whether the population increased over this period or decreased over this period. So generally, if I have a period AB, from A to B, PB minus PA would be the net change within this period or interval. But looking at the fundamental theorem, we know that this is integral from A to B of P prime of X dx. That is, if I have the derivative of P, if rather than having the total population, I have the change in population, I have the rate of change of the population, the derivative of that, then I can use it in order to get the net change in the population using the fundamental theorem. Make sense? And what would the rate of change in the population be? So I'm going to give you some graph to make it plausible in your mind that why the area under the rate of change would be the net change. So for example, imagine if you have P prime of T. So what you're given is the rate of change of the population. So for example, this is year 0, year 1, year 2, year 3, year 4, year 5. Yes. So for example, this is 1950. And for example, this is 1955. Yes. And what you have here is how much the population increased, how many people, how much the population changed during the year 1950. And then during the year 1951. And then let's say during the year 1952, there were more people who died compared to the ones who were born. So the population actually decreased in 1 year. And then there were this much change in the population the next year. And then again, let's say the next year, there were more deaths than birth. So the population decreased a little bit. So this is going to be the rate of change of the population. That's how population changed per year. It's a rate of change. If you want to get the total population, what would you do? You would have to just add up these values. Yes. So the ones that are above the x-axis, you need to add them up. The ones that are below the x-axis, you need to subtract them. So the total population until the year 1950 would be this plus this plus this minus this minus this. So the P prime of T could be thought of as the yearly change in population. It's a rate of change. Or you can make it finer, the daily rate of change of the population, or the hourly, or the second by second change in the population. You can create something for the whole world like that. And then as you're making the time intervals smoother and smoother, finer and finer, the whole graph is going to be smooth. And if you're looking for the net change in the population, you would only need to find the net area. So let's look at this example here. Population growth in Clark County at the 20th century, as the 20th century ended, Clark County in Nevada, dominated by Las Vegas, was one of the fastest growing metropolitan areas in the United States. From 1970 through 2000, the population was growing at the rate of. So what you have here, R of T, is not the total population. So this function does not give you the total population. What it gives you is the rate of change of the population, where 0 represents the year 1970 and 3 represents 2000. So it's T, that's the unit of measurement for time is decade. So where T equals 0 corresponds to the beginning of the 1970. Now, what was the net change in the population over the decade from 1980 to 1990? So 1980 would be represented by T equals 1, and 1990 would be represented by T equals 2. I am looking for population in the year 1990 minus the population in the year 1980. What I'm given is not P of T. I'm given R of T, which is the rate of change of the population. I'm given the derivative of PT. So this is going to be integral from 1 to 2 of the derivative function, which is given. So I would just need to calculate this definite integral. And since you're given R of T, it's going to be very easy. You just find an antiderivative of this function. You evaluate the antiderivative at 2 minus you evaluate the antiderivative at 1, and you get the net change in the population. So the population increased because this is a positive number. Is that clear? So if you have the rate of change, from the rate of change, you can get the net change. The net change formula, the net change in a function f over an interval from a to b is given by fb minus fa. However, if you're not given f, but you're given f prime of x, you can use the fundamental theorem, because this quantity here, which is the net change, will be equal this definite integral. Okay, let's look at another example. Production cost. The management of Stedler office equipment has determined that the daily marginal cost function associated with producing battery-operated pencil sharpeners is given by this function. So what you're given here is the marginal cost. You're given C prime of x, where C prime of x is measured in dollars per unit and x denotes the number of units produced. So the unit of measurement for x is just units, and the unit of measurement for the C of x is, or C prime of x, is going to be dollars. Management has also determined that the daily fixed cost incurred in producing these pencil sharpeners is $100. Okay, fixed cost. We talked about this before. Fixed cost is simply C of 0. That's the cost of producing nothing. $100. So basically, this is an initial value problem. You're given the derivative, and from the derivative, you can find an antiderivative, which is going to be the cost function. However, there is a plus C at the end, which you don't know, but you're given 1 point from the curve that will help you that arbitrary value plus C, the value of C. And if you have that, then you can answer part A and part B. Part A is, what is the cost of producing the first 500 units? So for part A, you want to know what C of 500 is. And for part B, you want to know what is the cost of producing the 201st through 400th units. So you want to know what was the cost of producing the second 200 units. So the first 200 units, whatever that cost, you're not concerned with that. You want to know the cost of producing the second batch of 200 pencil sharpeners from the unit 201 to the unit 400. So basically, you're trying to figure out what C of 400 minus C of 200 is. That's the net cost incurred by producing the second batch of 200 pencil sharpeners. So answering part 1, you don't need anything about the things that we talked about today. You don't need that. This is something that you already know how to solve, because if you have C prime of X, you can just find the derivative, antiderivative of C prime. You can get C of X, and then using this 1 point, you can find the function. So let's try to do that. I'm not going to write it because it's a very big function. I just write the antiderivative, which is going to be 0.5 zeros, 1, 2, 3, 4, 5 zeros, and then over, if I divide 6 by 3, I get 2x to the power of 3 minus 0.00, divide that by 2, I get 3x squared plus 4x, and then plus C, but that we know that C of 0 is 100, so C is going to be 100 plus 100. So that means you have the cost function. You can plug in 500 into that and get the answer. Is that clear? For part B, you would have to calculate this integral from 200 to 400 of C prime of X dx, because that will be C 400 minus C 200. That's the cost of producing the 201st through 400th unit. And that is also not very difficult because it's a polynomial. You can just get the antiderivative, which is over here, plug in 400, calculate, plug in 200, calculate, subtract, and you're going to get 552. You good? Any questions? Next example. So there is something common among all these examples that I'm giving you. And that common thing is that we are given the rate of change we are looking for the net change. That's the common theme of all these problems. Assembly time of workers. An efficiency study conducted for electronics showed that the rate at which Space Commander walkie-talkie are assembled by the average worker T hours after starting work at 8 a.m. is given by this function. So this function here, f of t equals negative 3t squared plus 12t plus 15. T is between 0 and 4. The unit of measurement for time is hour. And what this function is giving us is not the number of walkie-talkies that is produced by the average worker. It's the rate of change of the number of walkie-talkies assembled by each worker. So in other words, it tells us how fast the average worker works. I assume at the beginning of the day, maybe the speed is slow because the worker needs to warm up a little bit, and then after maybe 1 hour, he or she has warmed up completely. So we'll be able to assemble the walkie-talkies very quickly. And then as time goes on, maybe he or she gets a little tired, and their speed, the rate of change, how fast they are able to assemble the walkie-talkies, is going to decline. So that's my idea of how this will work. So if we graph this, it's going to be something like this. The question is, determine how many walkie-talkies can be assembled by the average worker in the first hour of the morning shift, in the first 4 hours of the morning shift. So what we're trying to figure out is the net change from 0 to 4. So we're trying to figure out how many walkie-talkies can be assembled by the average worker within the first 4 hours of the morning shift. So we're looking for the total. We're looking for the net change. So basically, we're looking for the area under this curve, which is going to be from 0 to within the first. It doesn't say within the first 4 hours. It is the function is given for the first 4 hours, but it says within the first hour. So here we are looking for this area. So from 0 to 1, negative 3t squared plus 12t plus 15 dt. We just need to calculate that. We are given the rate of change. We are looking for the net change. And it's a very easy definite integral to solve. You just find the antiderivative, evaluate that at 1, evaluate that at 0, and this will give you the answer. So the average worker will assemble 20 of these walkie-talkies within the first hour. And if you want to know how many he or she assembles within the second hour, you will have to calculate integral from 1 to 2 of the function f of t dt. And this is probably going to be different from 20. Within the third hour, you will have to calculate from 2 to 3 of f of t dt. Make sense? Any questions? Okay, let's do the next example. Projected demand for electricity. A certain city rate of electricity consumption is expected to grow exponentially with a growth constant of k equals 0.04. If the percent rate of consumption is 40 million kilowatt hours per year, what should be the total production of the electricity over the next 3 years in order to meet the projected demand? Okay. So there are some keywords here that you need to understand. First of all, the rate. The function is going to be the rate of electricity consumption. It's not the total amount of electricity consumed. It's the rate of change of electricity consumed. So it gives you maybe, for example, the daily or the hourly or yearly electricity consumed. It doesn't give you the total since a certain time. So this word here, rate, is a keyword. You're given the derivative. You're not given the original function. And the other thing is exponential. Any exponential growth or decay function has this form. F of t is, let's say, a times e to the power of kt, where k is called the growth constant, and a would be the initial value. A is the initial value. In other words, if I plug in 0 for t, I'm going to get a times e to the power of k times 0. That's going to be a times e to the power of 0, which is 1. So I get a. So with this information here, we can construct the function. The rate of change is going to have this form here, where it says the present rate of consumption is 40 kilowatts per hour. So the present at time 0. At time 0, the rate of consumption is 40. So that's the A times e to the power of kt. K is also given here. The growth constant is 0.04 t. So from the description here, we can write down the rate of electricity consumption function. Now, the question is, what should be the total production? So we are trying to figure out what should be the total production within the first 3 years. So if I plug in 1 into this, I'm going to get the production in the first year. If I plug in 2 into this, I'm going to get the production in the second year. If I plug in 3 into this, I get the production in the third year, and so on. So this doesn't give me the total production. This is the rate of change. In order to get the total production from time 0 until 3 years after, I will need to calculate integral from 0 to 3 of the rate of change function dt. That would be the total amount of electricity needed to be produced within the first 3 years. So if I calculate that, it's an easy function to find the antiderivative for. You just need to plug in 3 into the antiderivative, minus plug in 0 into the antiderivative, subtract, you get the answer. So before I give you some time to work on the exercises, any questions about this last one? I want to do one more problem from WebWork. Let's do number 12. I want you to get the common theme in all these problems. You're given the rate of change of something. You're looking for the total change in that. So it says a factory produces bicycles at a rate. Again, the keyword is rate. That's the rate of change. Bicycles per week. So F of t is 85 plus 0.5 t squared minus 0.5 t. This is, oops, f of t is 85 minus 0.5 t plus 0.5 t squared. Okay, so this is the rate of change of producing the bicycles, and t is in weeks. Now the question is, how many bicycles were produced from day 8 to day 21? Okay, so when t is 1, that would be day 7, because the unit of measurement for time is weeks. When t is 2, that would be day 14, and when t is 3, that would be day 21. Yes, so you want to know how many bicycles were produced within the weeks 2 and 3. So sorry, within the second week, the third week, and the fourth week. From day 8 to day 21. Am I right? Is it going to be the fourth week? No, from within the second week and the third week. Within these 3 weeks. So we're actually looking for the integral from 1 to 3 of the rate of change function, which is going to be f of t dt. And this should be easy because this is a polynomial. It's very easy to find the antiderivative. It's going to be 85 t minus 0.5 over 2 t squared plus 0.5 over 3 t cubed. And then I have to calculate the value of this function from 1 to 3. Let's take a look at the solution. Yeah. So we just need to plug in 3 into this function, calculate the value, minus, plug in 1 into this function, calculate the value, subtract, and you get 172.33 bicycles, which you round to 172 bicycles because you cannot have a third of a bicycle. Make sense?